Now let's look at a couple of examples where we calculate our primary measure of variation, the standard deviation. So we've got this really simple little example with just 4 data points in our data set. That's clearly not a large enough sample, but it's all we need to illustrate this calculation. Okay, so we can start by determining what some of our measures are. Our sample size, n, is 4. And we're going to need the mean in order to calculate the standard deviation. So let's get that. The mean, recall, is x bar, and we get that by taking the sum of all the individual data values and divide that by the number in the sample, or the sample size. Okay, so we have 2 plus 2 plus 3 plus 3 all over 4. So that's 4 plus 3 is 7 plus 3 is 10 over 4, which is 2.5. Okay, now recall that our calculation or formula for standard deviation for the sample is the sum of each individual data value minus the mean. We take that and square it, we add all those up, and we divide by n minus 1. That would give us the variance. We want the standard deviation, so then we'll take the square root. And it's handy to do this type of calculation using a table. So let's set up a little table. Okay, so we'll have our individual x's. Then we'll want to calculate x minus x bar for each one of those individual x's. And then we'll square that value. And we'll sum this column, and that will give us our numerator. Okay, our individual values were 2, 2, 3, and 3. So 2 minus 2.5 is negative 0.5, right? And of course this would be the same, so I'll just write negative 0.5. And then 3 minus 2.5, this results in a positive 0.5, and we get it again here. Okay, now I come back and take negative 0.5 and square that, and we get a positive 0.25. And this is positive 0.25. And of course the positive 0.5 squared will also give us 0.25 and 0.25. And now that numerator is the sum of all the x minus x bar squared. Oops, I forgot my bar, didn't I? Right here. There we go. So now let's sum this column, and of course 0.25, 0.25, 0.25, 0.25, that just sums to 1. So using our formula, we'll come over here, and our sample standard deviation is equal to the sum of the x minus x bars squared. Well, that's this sum at the end, bottom of this column. So that's 1 over n, which is 4, minus 1, and then we'll take the square root. So that's the sum of 1/3. And that turns out to be approximately 0.57735. But we want to use the rounding rule for standard deviation, and like the mean, it is 1 more decimal place than we had in the data. The data had 0 decimal places, so we will have 1. So this will round to 0.6. So the sample standard deviation is 0.6. Now these values are not too far apart, so we would expect our standard deviation, the amount of variation in this data set, to be kind of low. Alright, let's compare that with a second example. We'll go through the same calculations. Here our n is 4. Our mean is the sum of the values divided by the number of values we have. and again we get 2.5. So both data sets have the same mean. So mean is not enough to tell you what's going on in a data set. It's a good piece of information, but as you can see, without variation we can't really tell much difference in these data sets. Example 1, values 2, 2, 3, 3, they were pretty close together. In this example, the values 0, 0, 5, 5 are pretty far apart, 0 to 5. So we would expect to find more variation, even though the means are the same. Let's set up our table again. We'll have our x's, our x minus x bar. Then we'll square that. So you see, you really don't have to memorize a formula if you kind of learn the steps for the table. Okay, we had 0, 0, 5, 5. So 0 minus 2.5 is negative 2.5. So this one's negative 2.5. And 5 minus 2.5 is positive 2.5. And this one is 2. So now we take our negative 2.5 and square that, and we get positive 6.25. This one's 6.25, it's the same. When we take positive 2.5 and square that, we still get 6.25 and another 6.25. So our numerator is the sum of the x minus x bars squared. When we add all these up, we get 25. So our standard deviation is equal to the sum, add them all up, of the x minus x bar squared, that's 25, over n, which is 4, minus 1, and then the square root. So it's the square root of 25 over 3, which is approximately 2.886, or again, rounding to one decimal place, one more than what we have in the data, 2.9. So what we have seen here is these two data sets that had the same mean but very different standard deviations, 0.6 and 2.9. Relative to the data, this is clearly a larger amount of variation, and that's what we actually see when we look at the data. So another thing to note is that standard deviation, you can clearly see, can never be a negative number, because even when we get a negative result here for x minus x bar, we square, and these are all positive, so this sum will be positive. We could have a 0 standard deviation, but the only way that can occur is if all the x's are exactly the same as the mean, which of course they would be. If every value is 5, 5, 5, 5, the mean would be 5, and we'd have 5 minus 5. These would all be zeros. 0 squared is 0. Our numerator would be 0, and our standard deviation would be 0. That's very unusual, and I don't expect us to encounter that in any of the examples we'll do in our course.